let's go ahead and get started. You've got a homework assignment due on Friday, and then looking at the project, the final submission for that is on the 12th of April. I'll be returning your calculations for the reservoir sizing today. I've had a chance to look them over and have a few comments. For the most part, it looked really good, although I didn't look at any of the financial calculations. I was just looking at the sizing, which is what was due. So hopefully the project is going well. I know that a couple of people have been tinkering around with some advanced features of the program. A few people have independently discovered the Darwin Designer feature, which is really interesting, but ultimately probably more work to learn than the time that it saves for a single project. For more projects, it's definitely something that is worth knowing. We'll get into that later. Just about reservoir sizing, on a couple of papers I made the note that including a brief summary of the method that you used would have improved the submission. And that's not because I don't understand the method you used. We all use the same method, the approach that I outlined in class. It's just that when you're working on a project, whether it be in college or really especially after you graduate, you need to make notes so that you can remind yourself how you did something 6 months in the future or a year, 2 years in the future. You'll maybe be really closely working on something and understand the ins and outs of it really well, but then sort of forget how you did your calculations. And so it's a good habit to be in to document what each column means in a spreadsheet or how you calculate it. Even if you have the formula in the spreadsheet, it's really a helpful thing for you to, in the rows below the spreadsheet, give yourself just the shortest description of how it was calculated. Now, one thing I wanted to point out is there's somewhat of a mental shift in the way that assessment is done from a homework to a project. You know, when your homework assignment is graded, really the only thing being evaluated is whether it was correct or incorrect. Students who are sloppy and have hard to read handwriting and their drawings are no good generally get the same points as someone who does a really effective and thorough job, because the only thing that's really being evaluated in a homework assignment is usually whether it's correct versus incorrect. But on a project, really the question you have to be asking yourself is, what can I do to make this submission better? How can it be improved? And so you don't get a perfect grade on a project just because the answer was correct, but you get a perfect grade on a project because the answer is correct and it communicates information clearly and is well organized and concise. So obviously correct versus incorrect is one of the assessment measures that's applied to a project. And so we'll be looking at whether the calculations are right or the right method was used. But when a design can have multiple correct answers, part of what's assessed is how well optimized is the project. Is every pipe as small as it could be, or are there pipes that could be optimized further? And so the design outcome is one of the things that gets assessed there. We can be looking at whether the presentation of design calculations is organized versus disorganized. And I didn't put this in your handouts, but if you want to write down some of these different things that I'll be looking at in your final submission, I think it'd be useful for you to keep in mind as you're putting everything together. Because in the draft submissions, I've been looking at mostly just, are you doing it right? But at the final stage, when I'm looking at a whole view of the project, I'll be looking to see more than just whether it's correct, but I'll also be hoping that you have an optimal solution, that it's disorganized, that it's organized, rather. That the figure quality is clear rather than being unclear. I hope that your approach is well documented, and that doesn't necessarily mean that it's really wordy. Well documented just means that if you come back to something later, are you going to be able to understand quickly what you did, or you're going to have to teach yourself all over again how to size a reservoir, for example. In fact, I prefer that reports be concise rather than unnecessarily verbose and just sometimes the detail is too the explanation is too detailed. One of the things that's probably the hardest to know when you're a young engineer is whether your effort's been appropriately invested. Sometimes someone will spend, and this has happened on this project before, 15 hours on getting just perfect, really great demand estimation, but then has done so much time and effort on that they get burned out and then do really a minimal job on optimization and financial calculations. And so that would sort of be a misallocation of time where the resources and the effort was not deployed wisely. And when you graduate, maybe you'll be working for a design engineer that's billing clients on an hourly basis. Your clients will want to have project billing reflect their priorities and not spending too much time on things that really have diminishing returns. In engineering economy, we talk about how you can have a really detailed cost estimate, but it can cost a lot of money to generate a detailed cost estimate, and often if you spend too much time trying to save a couple of extra dollars, you've actually wasted more than you've saved. Maybe you've noticed that if you are thinking of buying a new computer and you go from store to store and you're researching it online and you spend 10 or 15 hours finding the best computer and finding the best deal, but then you only save maybe $20 or $30, then that wasn't a good use of your time. So ultimately, the main point I'd like to communicate to you is that as you're preparing the final project, what I really hope is that it reflects the best that you can do. Not just that it's technically correct, but also that it's clear, it's organized, well-documented, concise, and has all the attributes that can allow me to give it a nice high grade, which is what I'm sure all of you are going to hope for and will deserve. All right, so, boy, I'll step down off the pet talk soapbox and we'll get back to hydraulics. The first thing I want to point out is an underflow gate, because we've talked about chokes. We've talked about how a choke can occur when a channel gets too narrow, or a choke can occur when a step occurs, a step up in the channel elevation. But an interesting additional feature that can cause choking is when a gate is lowered into the flow. And so this is a case where previously there was some channel bottom and water was flowing along, and a gate was lowered into the flow, interrupting its flow, and eventually, when the gate got low enough, it started to cause pooling under the gate, and then water was coming up from the level that it exits the gate there. And so this is a special case that we'll return again when we do a couple of activities back in the lab. But I wanted to point out the case of an underflow gate acting as a choke because it can raise the water upstream. If you compare this to a step up has the capacity to accumulate trash on the upstream end of, can be called a sill when there's a step up. And so sediment can accumulate there, and it's not adjustable usually, the height of the step up. But as a flow control device, an underflow gate avoids both of those disadvantages. It is adjustable, and sediment won't accumulate on the bottom of the channel when you have an underflow gate. And the other advantage is that, remember that if we have the step up equal to or greater than the maximum delta Z, then the flow that goes over that will be critical. Remember, when cooling occurs because of a choke, the water level will rise until there's enough specific energy to get up over the obstacle. But it will only rise until you've got the critical depth over the obstacle. And critical flow is a little bit unstable. And so that's a disadvantage as well in this situation, is that the cooling has occurred until critical flow exists over the obstruction. In the case of an underflow gate, another advantage of this compared to using a sill to control flow is that you don't necessarily have to have critical flow coming out of the gate. The water coming out of the gate may be supercritical, it may be subcritical. You have a variety of different options available for the downstream depth. So I wanted to point out the way that we go through and calculate conditions at an underflow gate, and the reason why is that this interacts with the principles of specific energy that we've been using so far. And so we'll start this off by considering a flow rate of 36 cubic meters per second. So let's say for Q is 36 cubic meters per second, and a channel width of 4 meters. I don't think that this is noted on the slide itself. What we do know on the slide is that the initial depth before the gate was lowered into the flow was 3.5 meters. And so Y1 of 3.5 meters, that's the initial depth. And then on the figure where it says that the Y prime 1 is unknown, what we're interested to find out is the depth after the gate is lowered. All right. We do know the water depth after the gate. And so Y2 is the 0.7 meters. We could call that Y2 prime, but that's a little bit redundant. Y1 was a constant depth all the way through the channel before that gate was put into place. And so there really wasn't any 1 versus 2 because the depth was constant. So this is the downstream depth. So a first step will be for us to find the flow per unit width, flow rate divided by the width, and that is 9 meters squared per second if we divide the 36 cubic meters per second by the width of 4 meters. And we want to find the energy at 2, which is a little different from how we often start by finding the energy at 1. But this E2, the energy at 2 is going to be the energy required for flow. That is, downstream, there's a certain amount of specific energy that's required to convey the flow through the channel, and we want to find out what that is. It'll be Y2 plus lowercase q squared 2g Y2 squared. And we've seen this expression before for velocity depth. So it is the 0.7 meters of depth, 9 meters squared per second, squared divided by 2, 9.81 meters per second squared, and 0.7 meter depth squared. And that total amount of specific energy of 9.125 meters, that represents E2 required for flow. We're going to find out if the original amount of specific energy available can provide that, or if cooling had to occur. When we start lowering the gate, the water won't begin to rise the second that gate hits the surface. It might be that there is enough specific energy to begin with, that the water can simply accelerate under the gate and make it out without any kind of choking. But if we put the gate deep enough down, then there will be too much energy required at 2, and cooling has to start to occur at 1 in order to provide that energy. And so the water will begin to get deeper in order to make it so that the available energy is equal to the required energy. So our first question is, how much energy is originally available? We'll find E1, Y1 plus lowercase q squared divided by 2g Y1 squared. The original depth was 3.5 meters. And so when we put the velocity head term in with it, that means the original specific energy available is much lower than what's required for the flow to get under that gate. To get under the gate, the water's going to have to be moving very fast. It has a huge velocity head. I mean, if you look at the energy that's required, there's only 0.7 meters of depth and almost 9 meters of velocity head. And so there's really a lot of velocity head after the water has gone under that gate. And so it's requiring so much energy for it to speed up under that gate. We don't have that much energy available before, back when the depth was 3.5. And so choking will occur. Since E2 is greater than E1, choking will occur. Comparing energy. So what we'll say is, when do you think it'll stop, the water level will stop rising?
When the energy basically not what you thought.
Brilliant, that's right. So E1 prime will equal E2. It's going to keep cooling until there's enough energy that it can get under that gate. It's not going to keep cooling. As soon as it can achieve that, then it'll stop getting deeper. So what we need to do is we need to say 9.125 meters will equal y prime 1 plus q squared divided by 2g y prime 1 squared. So we're going to solve for what is that mean depth that will give us the 9.125 meters of energy that's needed. Okay, so if we substitute in the values that are known, we get an equation that's y prime 1 cubed minus 9.125 y prime 1 squared. That's confusing, right? Y prime 1 squared, especially with my chicken scratch handwriting, but we'll soldier through. 4.128 is equal to 0. So this is the equation that we get, and then the roots of that are negative 0.65, 0.7, and 9.075 meters. Do we need to assess the flow regime to find out critical versus subcritical? Because what we've done previously, remember when we were looking at 1 versus 2 for a channel getting narrower or a step up, we would say we choose the route that is associated with if there is subcritical at 1, then there will be subcritical at 2. So should we apply the same logic here? Should we say if there is supercritical at 2, that must mean there's going to be supercritical at 1 and vice versa? Why not?
Because you know the water level has to rise to keep out of energy.
Okay, so you're going to use common sense that it can't rise to 0.7 meters because that is not rising. That would be falling, right?
Yeah.
And it can't rise to negative 0.65 meters because that's also the wrong direction. And not real. Well, real, but negative. So yeah, it's definitely going to get deeper. But actually, if we had diagnosed the flow regime downstream, that would be the wrong thing to do, to draw that same conclusion. Because when a channel is having the step up, that's when we'd say, well, subcritical equals subcritical. You know, if we had subcritical conditions at 1, then they'd be subcritical at 2. You know, the elevation is going to change a little bit. Or if the channel was getting narrower, that was also a situation where we consider what's at 1, diagnose the flow regime at 1, apply the same thing at 2. Well, in this case, it's supercritical flow of 1. I'm sorry, downstream at 2. Under the gate, it's moving really, really fast. I mean, you can tell this velocity head is huge. 0.7 meters of depth and more than 8 meters of velocity head. So the water's moving supercritical under the gate, but it's subcritical at 1. So this is a case where this kind of obstruction has actually changed the flow regime from subcritical to supercritical. Does that make sense? Well, no, because the choking increased the depth upstream, but it already was subcritical to begin with. And so the change, the fact that it's now supercritical downstream, that's the change. And it's just because of that physical gate structure. The water has to come out at the height of the gate. And if this is the critical depth, you know, it's going to go down. And so the flow is subcritical as long as it doesn't go below that imaginary line of the critical depth. But as soon as the gate is lowered below the critical depth, the water has to come out where the gate ends. And so it's forcing that downstream depth to be equal to the gate opening height. So it's really just because of the gate itself. And it's really fun when we get to play around in the lab with flume and force the flow to go critical out of the gate. You know, we have this in the lab. We have a sluice gate, and we'll be raising it and lowering it and watching the flow all of a sudden be going from uniform flow, and we'll start to choke it, and the water will start to pool upstream. And even when it's choked a little bit, it still won't be supercritical downstream yet. And then we'll put the gate further down, and all of a sudden it'll start to be supercritical at the downstream location. And as soon as you have supercritical downstream, then you get the hydraulic jump a little further beyond that. And that's the real magic. So
what happens in a scenario where there is enough energy upstream to make that happen? Well, let's say there's more than enough. Does that water level come up past the gate bottom?
There isn't enough upstream, or there is?
So we said the upstream was 3.837. Let's say on the downstream it was 3.5. So there was enough without it pooling.
Okay, then it won't pool.
But would the water level past the gate rise, or would there just be extra energy?
The water level would be unchanged.
Oh.
It would stay there. It would be like this. The two water levels, let's say, I've sort of mixed up all the colors now. Here's the gate. The water level would be like this.
Oh, okay.
It would be flowing up under there, and there'd be some turbulence here. It looks, you know, it'd be look unsettled, but the water levels would be the same. Other questions? Other question ought to be, when do we get to see a hydraulic jump? I'm glad you have patience. Your patience will pay off. Oh, there it was. All right. Broad-crested weir. So the other thing today is introducing weirs, and a broad-crested weir is a step up that's just temporary. It steps up for a little bit and it drops back to the original channel bottom elevation. And so the way that it works is the delta Z, or in this case the notation is given as H sub W, the height of the weir, is raised so that it induces critical flow over the weir. Why? Why would we want to have critical flow over the weir? Well, we know something about critical flow. We know that on the specific energy diagram, that critical flow corresponds to E minimum. And so by having this step, a broad-crested weir, the whole point of it is to force critical flow over the top of the weir so that you can measure what's the depth. Because if you measure the depth, then that allows you to quantify the flow rate. It's a useful thing to know. Remember the expression y sub c is equal to q squared divided by g to the 1/3 power. You remember that, right? You know, it's really hard to know what is the flow rate in a channel. I've just been giving you, let's say the flow rate here is 36 cubic meters per second. Let's say the flow rate is this or that. Well, out in the real world, in a channel, you can't just look at the flow and know what is the flow rate. And so this is a flow measurement device, a broad-crested weir. And the trick is, if you force critical flow over the weir, you know Y sub C and can measure it, then from that you can find the flow per unit width, and once you know the flow per unit width, you can find the flow rate through the channel. And so this is a flow measurement device, and the disadvantage of it, as I mentioned in the previous slide, is that trash can accumulate downstream, and you force the flow to go critical over the broad-crested weir, and that can be unstable. The disadvantages of the instability we'll get into a little bit later in the semester. And also, it's not convenient to raise and lower the height of the weir. And so you may have a very low flow rate of water going through there. And so if the water level is really low, but you've got a high broad-crested weir, then cooling would have to occur in order to use the weir. And so it's not very flexible. Disadvantages, inflexible. Disadvantage, trash accumulation. But the way it works is by forcing critical flow over the top of the weir.
So in like a large channel, would this be a big,
It'd be the entire width of the channel.
and it's just for flow measurement?
Just for flow measurement.
I mean,
Yes, that's all it's for.
it just seems like,
I know, I've been leading you astray by trivializing how easy it is to know the flow rate in the channel. I've been saying, let's say that it's 36 cubic meters per second. Well, that's usually a huge mystery. How much water is going through that channel is something that has stumped farmers and engineers alike for hundreds and thousands of years. Then they figured out that if you measure the depth of the critical flow, you don't have to measure the velocity. I mean, you can try to find out the flow rate in the channel by saying Q equals VA, and even when the flow isn't critical, you could measure the depth, measure the width, and then try and estimate the velocity. But estimating the velocity, what do? Throw a stick on top and then like measure how quickly that stick is floating over the surface? Well, that's great, except for velocity distribution. And the top of the water is moving faster than the bottom of the water. And so it's really hard to estimate the flow rate in the channel, but then if you know that's critical flow, everything falls into place really easily. Yeah.
So you said the weir has to be all the way across the section. So why can't you have like a section just in the middle? Because it's affected like three-dimensionally. I understand that.
Right. So let's do a top view of the channel. So you're saying why not just have the broad-crested weir be part of the channel width? That's your question?
Yeah.
It's because, yeah, it maybe would be critical over here, but some of the flow would be diverted around the obstruction, and that would change there wouldn't be a uniform flow per unit width. It would, you maybe would know the lowercase q here, but you'd have a different q here versus there. So it would cause imbalances in the flow per unit width spatially across the width of the channel.
so do they have to be a certain size, a certain height, compared to how much water is being?
Yeah, that goes along with the disadvantages, is that remember that there is some obstruction that won't cause critical flow. Like just a small obstruction, let's say here's our channel and here's the bottom of the channel. If we just put in a little bump, I mean, maybe it'll go down a little, but it's not going to get to critical. We have to make this a certain height before it's going to drop the flow down to the critical depth. So they do have to be delta critical or delta Z max. Sometimes we've been calculating how tall can it be before choking starts to happen. And so really there's only one perfect broad-crested weir height for a certain flow rate. Anything less than that isn't going to cause the critical depth, and anything bigger than that is going to cause a little bit of choking.
So it's better design for choking. The
Yeah.
assumption that as more water comes, it's going to change.
Because, I mean, you've really got no other choice. You can either make it too big, which will cause choking, or if it's too small, it won't induce the critical depth, and in which case you can't use it for measurement. The only way you can measure is if it's critical depth going over the broad-crested weir.
I actually have two questions. One, is there any broad-crested weirs around here?
Probably.
And the other one is,
I'm so ignorant on local flow structures. If we were in Utah, see, that's where I went to grad school, and I knew where all the canals were. My professors were better at taking us on field trips. We'd get in vans and go look at drainage canals and stuff, but I haven't scouted out the drainage canals around here. Yeah, so, your second question?
on bridges, I noticed there's elevation markers.
Uh-huh.
Are those used in some way like that, or is that just for height or?
They're usually trying to know what the stage is for flood control purposes, and just they know that when the water level gets to a certain depth, that somewhere along the banks, water will be flowing over. And so I think that usually they have a curve that relates stage to Q. You know, there is some curve, but it's not necessarily that there's a broad-crested weir at the bridge. They haven't installed a broad-crested weir. I mean, they have some other relationship that allows them to know Q versus that right there. All right, so look at the values here. H is the distance from the top of the broad-crested weir up to the energy grade line, and that 2/3 of H is the critical depth. Remember that minimum specific energy is 3/2 of the critical depth, and this is related to that. This is saying specific energy is the depth plus the velocity head above some surface, and so specific energy is the E. E is what we've previously been referring to as E is represented here as H. I took this from a different text, this figure. And there is a C sub D. It's a coefficient of discharge, and it's basically an energy loss coefficient. You have to correct for energy loss because there's turbulence caused by this flat surface here. It interrupts some of the flow, and so a typical coefficient of discharge may be in the neighborhood of 0.6. And so you can know the flow rate in the channel by simply knowing the width of the channel and then knowing how much specific energy there is. Well, how much specific energy is there? It's a function of the critical depth, which is what you're measuring over that broad-crested weir. And you can calculate coefficient of discharge by the ratio of the height of the weir to the specific energy. And so you can see that H versus H sub W is what goes into there, but a typical value is about 0.62. Broad-crested weir, sharp-crested weir. The difference is how long is the weir. You notice that this is some value L, relatively long. It takes a while for the flow to set up. Maybe what I ought to do is, we have a broad-crested weir back in the lab. Maybe I should put it in and make one of your homework assignments to go take a picture of it when it's running, just so you can see it. I mean, it wouldn't be anything other than that, but we have a little broad-crested weir. It's a wooden piece that fits into the channel. And it's not like as soon as you get up here, it instantly drops down to the critical depth. You've got to have it be kind of long because it gently transitions, and then it finally gets there. And then it sort of flows over and reestablishes its flow depth again. So it's a little bit of an art. Typically what I say to students is you go 2/3 of the way along the broad-crested weir, and then that's where you measure the critical depth. We've had good luck with 2/3 of the way measuring the depth there and finding the critical depth. So it has some certain length to it, but a sharp-crested weir comes to a point. It comes to a sharp crest, we could say. And the way to look at the sharp-crested weir is to compare the energy at 1 versus 2. And here we're talking about the specific energy, the energy above some common datum for the 2 points. And so there's some elevation, water surface elevation above the crest height and the velocity head. And so H in this figure means specific energy. It means the depth above the weir, and the velocity head, those two things. And then consider the same thing at 2, but you happen to choose 2 so that it's coincident with the elevation of the sharp-crested weir. That means that there's only going to be elevation head at 2. And when you do that, when you pick an elevation at 2 equal to the sharp crest itself, you can find the velocity of the water at 2 as a function of the depth at 1 and the velocity at 1. So making some rearrangements of specific energy, you find that the velocity at 2 is the square root of 2gh, and where h is the total specific energy. Okay, now thinking three-dimensionally, remember we had to make the broad-crested weir the whole width of the channel. That won't work. Well, here, a sharp-crested weir, that is the full width of the channel, we call that a suppressed weir. Suppressed. And the reason why it's called suppressed is that there are some contraction effects that are suppressed when you make the weir the full width of the channel. But you don't have to make the width the full weir of the channel. The weir the full width of the channel. It's a little different from the broad-crested weir. Actually here, we can have the water flow over just part of it. So in contrast, what if the water was just flowing over the weir crest, wasn't the whole width of the channel? Channel width is one thing, and then this is the weir crest. That width is another. So that's an unsuppressed weir because it does not suppress contraction effects of the nap as it flows over the weir. Let's consider some differential height of the water as it's flowing over the weir. Here in the case of the full width, the flow rate, Q, is VA. And so the change in flow rate for this differential element is going to be the velocity of that element multiplied by the differential area, which is just some very small incremental increase in height multiplied by the width of the channel. And so, what is basically the flow rate equation for this is where this derivation is headed. If we integrate from 0 up to the total height of the water, of the elevation above the weir crest, then we have 2/3 of square root of 2g times L, which is the length of it, and the height of the water to the 3/2. But just like in the broad-crested weir, where there's energy losses, coefficient of discharge, we have to apply a coefficient of discharge here as well, because there's drawdown effects, friction losses, contraction losses, and again, a typical C sub D is around 0.6, but you can calculate the actual C sub D as a function of the height of the water over the weir to the height of the weir itself, H to Z. And so that's how you can estimate a coefficient of discharge. They're experimentally verified in the lab. We can sometimes calculate what is the actual C sub D by calculating the flow rate that's predicted and then measuring the flow rate in the lab with stopwatch and that graduated tube. But that's how you can find the flow rate with a sharp-crested weir. And sometimes we simplify it even a little bit further. We combine the 2/3, the square root of 2g, all of that's constant, and even the C sub D is typically around 0.62. So if we just say, let's combine all of that together in one master C variable, then in BG units you commonly see the sharp-crested weir equation. It's just simply 3.32 L H to the 1/2 power and 1.84 for SI units. Here's the unsuppressed weir, sometimes called a contracted weir, and it's a little bit different. Same principle, but we have to calculate a modified weir length. You notice that here in the formula is L prime instead of L. So here it was just L. For the full width weir, you use its actual length. But for a unsuppressed weir, you have to find an effective flow area. And the formula to find the effective area, and effective is because of the effects of contraction, and it's simply a function of how high the water is relative to the length of the weir. And so you can calculate L prime with this formula here and then find the flow rate through an unsuppressed weir. One thing that's interesting is that in a, let's see if this is a, here, this nap, it's called a nap, the water that flows over the weir, and it's kind of like a sheet of water. Air can get trapped underneath the nap. There can actually be a vacuum under the nap, because when the water starts to flow over the edge, when it's just a trickle, okay, so here's water, and it's just a trickle. It's going like this. But when the water level gets higher, it's going to be flowing over more, and so there's not enough air under here because it's the full width of the channel, and so the waterfall starts getting bigger and bigger, but there isn't any venting up under the nap. And so sometimes one of the effects that goes into the coefficient of discharge that's used for sharp-crested weirs is a vacuum underneath the nap that's artificially pulling it down, where if you vent in there, it would cause the nap to raise a little bit because there isn't a negative gas pressure underneath the nap. That's one of the reasons that these contracted weirs are sometimes used, is that when you've got it contracted like that, then that does allow for positive ventilation underneath the nap. Here's a spillway. This is a really tall dam. I think this photo is taken in Oregon. The Grand Coulee Dam, if I'm not mistaken. And what it shows is that the water is moving at an incredible rate over the spillway. This is very vertical, and so that's going to cause supercritical flow. And then once it reaches the channel downstream, it's got all this energy that has to be dissipated. So there's a hydraulic jump. That's how the energy is dissipated. Overflow spillways also have calculation formulas that look similar to a sharp-crested weir. In fact, we're going to model this spillway as a sharp-crested weir. You can see that the equation 3.32 times LH to the 3/2 power for BG units. SI units, it's 1.84 rather than 3.32. But the reason why we would translate that into 3.97 and H sub D is that there's a rounded spillway crest. And so the difference between H and H sub D is where we account for where does the sharp crest end and where does that rounded surface begin. And we differentiate between the effective sharp crest and the more rounded spillway crest that occurs, just to sort of make sure that there isn't a jump of water going over the edge. You have to have a rounded surface there to guide the water over the spillway, so that you want it to continue to maintain contact with the spillway and not sort of go over and then, like little kids do when they're going on a slide really fast. They sort of get a little bit of air. You don't want that to happen over the surface of the spillway. And so that's why the spillway crest is curved.
In this example, we're going to try and determine the elevation that the spillway crest should be built at for a 300-foot long spillway that's going to be carrying a flow of 38,000 CFS. After finding the elevation of the spillway crest, we'll then consider the theoretical elevation of the elevation of the theoretical weir crest. This is the example where we are considering a spillway that is to pass 38,000 cubic feet per second. and the length of the spillway is 300 feet. The question is, what elevation to build a spillway crest? What we know for quantifying the flow rate of this spillway is the equation that relates the length of the spillway and H sub D. Well, we can rearrange that expression to solve for the H sub D that we ought to have for the flow rate that's been given. And substitute in the values that are known. And from that find, the H sub D needs to be 10.06 feet. The interpretation of that is that the spillway crest should be 10.06 feet below 4350. That's the elevation that we know other things are going to be built, and we don't want the water level to go any higher than that. So in other words, 4339.94 feet is the elevation to build the spillway crest. The other question that's asked is, where is the theoretical weir crest? So to address this second part of the question, we simply look at the sharp-crested weir equation, because we're going to find the theoretical crest of that sharp-crested weir. And again, can rearrange the expression to solve in terms of H. And substitute in the values that are known. H is 11.33 feet. So the elevation then is the water level of 4350 feet minus 11.33 feet, and that's equal to 4338.68 feet. That is the elevation of the theoretical weir crest.